Welcome to another science video. My name is Jeremy Krug, and in this series we're learning about waves. And in this specific video we're learning about some applications of electromagnetic waves. It looks like I'm floating out in space here, but actually we're learning about the colors that we're seeing in these different galaxies. Now, if you're not familiar with this particular image, this is a picture or an image taken by the Hubble Space Telescope several years ago. And this is something called the ultra deep field, where we basically pointed this space telescope into a pocket of space where we didn't think there was a whole lot of anything, and we actually found hundreds, if not thousands, of galaxies that are out there in space. Now, as you look at this impressive image here, I want you to notice for a moment the colors of the different galaxies. So we have some galaxies that look like they're almost kind of a pale blue color. There are some that have what look to be kind of an orange or a yellow color. There are several that have this almost a ruby red color if you look at these here. In fact, a lot of them have this ruby red or dark red or a reddish type of a color. Now, when we think about these, we know that galaxies are not just blobs. They're not just individual stars. Galaxies are made up of millions, billions, and possibly even more than that as far as stars go. And so when we look at these galaxies, we have to ask ourselves, are the colors that we're seeing in this image the actual colors of these galaxies? Is there a reason to believe that these galaxies actually are red or that they're actually blue? Are these the real colors we're seeing? And the answer to that question is probably not. It's probably not the case that this galaxy right here is actually ruby red. It might be because the colors that we're seeing here are actually distorted. Now, a couple of videos ago, when we were learning about sound and how sound can be distorted, whether you're moving toward the source or moving away from the source, well, that concept can work for electromagnetic waves as well. We call that the Doppler Effect. You might remember that we said that if you're moving toward, or an ambulance siren is moving towards you, it's kind of distorted to make it sound like the pitch is higher than what it actually is. And likewise, if you're moving away, or the siren is moving away from you, it's distorted to make it sound lower than what it actually is. And guess what? The same thing happens for this light. When a galaxy moves towards us, let's imagine that we have a galaxy here, and I just found a couple of random pictures of galaxies on the internet. So here we have a galaxy, and it's giving off light. So we can imagine the waves here. And here we are on the Earth. So when the galaxy moves towards us, and this is of course exaggerated, notice that we are seeing more waves. We're perceiving more wavelengths and therefore a higher frequency than that galaxy actually emits. So what that means is, if the galaxy is moving toward us, the frequency seems higher than it would otherwise be. Now, if we go back to the electromagnetic spectrum that we looked at in the last video, that means that the light from that galaxy right here would actually look bluer than it really is. So if this is the real overall color of the galaxy, then it might look more like this. It might have a blue tint to it. Now, I'm aware that this is actually a different type of galaxy altogether, but it might have this type of a tint to it. It might look bluer. Now, that's something that we call blue shift. The perceived color of a light-emitting object like stars or a galaxy looks bluer than what it really is when it's getting closer to you. So we would say that if something is getting close to you or closer to you, that the color is blue shifted. It is blue shifted. Well, what about the opposite? What happens when a galaxy is moving away from us? Well, here is the other possibility. Let's say we have the same galaxy, just for argument's sake, and here we are on the Earth, and it's giving off this light, but now the galaxy is moving away from us, like that. Well, if that's what's happening, then we're going to perceive fewer wavelengths than what actually is being emitted. So it's going to look to our eyes, to our telescopes, like it has a lower frequency than the light the galaxy is actually emitting. And so that means the frequency seems lower, and to our eyes, to our telescopes, the light is going to look redder than it actually is. And so this galaxy, and I'm aware that that's a different galaxy and a different type of galaxy altogether, but the galaxy might look like this. It might actually be emitting overall light like this, but it might actually look redder to our eyes, to our telescopes, because it's moving away from us. This is just the Doppler effect. It's the same thing as the ambulance that changes pitch depending on if it moves away from you or closer to you. The color is different based upon if the star or the light is moving close to you or moving away from you. So the perceived color of this light-emitting object, the galaxy in this case, looks redder when it's moving away from you. This is called redshift. So we have these two phenomena that are actually pretty important. We have blue shift for things that are getting closer to us, and there's red shift for things that are getting farther away from us. Now, what do we know about the light from galaxies? Let's try to put some of our information together. Well, we know that about 100 years ago, in the 1920s, the American astronomer Edwin Hubble was the first person to discover that most galaxies emit light that is redder than what it seems it ought to be. And so that means that we can say that most galaxies are red-shifted. Now, if most galaxies are red-shifted, then what does that mean? Well, from what we know about the Doppler effect, and this is fairly simple physics here, it tells us that most galaxies are moving away from us here in our own Milky Way galaxy. So if galaxies are moving away from us, most galaxies are moving away from us, well, it's interesting that the farther away that a galaxy is, the faster it is actually moving away from us. Well, put all that together, it sure sounds like we can come to a logical conclusion that the universe is expanding. It's like a beach ball. If you take a bunch of marker spots and put that on the beach ball and start blowing up the beach ball, well, all those marks or all those spots keep getting farther and farther apart from each other, right? Well, that's kind of what's happening in our universe here. The different galaxies are moving farther away from each other for the most part. So our universe seems to be expanding. Now, let's think about what this means. If the universe is expanding, then there are a few things that must be true. If the universe is expanding, then that means that our universe is larger today than it was yesterday, right? If it's constantly expanding. And if that's the case, then that means that our universe at some point in the past was much smaller than it is today. And based upon simple physics, inertia, we know that the universe has been expanding for as long as it's existed. Now, it's a little bit more complex than just simple inertia. But we know from other laws of astronomy and physics that the universe has been expanding for pretty much as long as it has existed. This tells us that at some point in the past, the universe was actually extremely small. Now, how small was the universe in the past? Well, there is evidence to believe that it was extremely, extremely small. In fact, almost 100 years ago, the astronomer Georges Lemaitre was the first one to propose that at a specific moment in the distant past, our universe was actually microscopic in size. And then it began to expand at a very rapid, a very fast, yet a very controlled rate. And this explanation for why our universe is redshifting in the way it is came to be called the Big Bang Theory. Now, it is currently believed that the universe is between 11 and 14 billion years old. Most scientists would say it's right around 13.8 billion years old. Now, it's interesting that the astronomer Georges Lemaitre was trying to understand how the universe came into being. He was actually an astronomer. He was also a priest, as it turns out. And this idea, the Big Bang Theory, by the way, he did not coin that term. That was coined by someone else several years later. But it's kind of a misnomer, because when we say Big Bang, first of all, according to all of our scientific evidence, it wasn't big at all. If we're saying the universe started out very, very tiny and then began to expand very quickly, well, we're not talking about something that was large. It was something that actually started out very small. Now, the bang part is also somewhat of a misnomer as well. We're not talking about something that was somewhat of a disorderly explosion necessarily. We're talking about something that was an expansion, a rapid expansion, something that we can actually calculate most of. It's actually quite interesting how we can look at the temperature and the actual residue, the actual electromagnetic residue from the Big Bang that we still see. If you look at static on a TV screen, for example, if you have an old style TV and you tune around trying to find TV static, some of that TV static is actually residual electromagnetic radiation from the Big Bang that's still out there. Now, when we talk about electromagnetic waves in our society, there are so many applications of them. And I want you to know about the expansion of the universe and the applications and how we know the universe is expanding. It helps us to appreciate how small we really are when we think about how big the universe is and how long it's been around. We can think about radio waves and how those are used. They're, of course, used in radio broadcasts and television broadcasts as well. We can think about microwaves. We know that they're used for cooking, of course, in microwave ovens, but microwaves are also used in your cell phones. If you have a cell phone, it is able to communicate with the cell phone tower by a little transmitter in your cell phone. Basically, it's a glorified radio transmitter, which operates in the microwave band of the electromagnetic spectrum. Infrared light. We can use infrared in TV remote controls. If you have a TV remote control, you hit the button, it communicates with the TV or the DVD player or your cable box, whatever, by means of an infrared light. A lot of heat lamps are actually infrared light. You most of the time, you can't see infrared. Very, very few people can actually sense any infrared light. We can usually sense infrared light as humans as heat. It actually feels hot on your skin. So this is actually used for heat lamps. It's used for thermal imaging. If you've ever used night vision goggles, most of those night vision goggles take advantage of infrared light. We have ultraviolet light as well. Ultraviolet light is used for sterilization. If we have, for example, in my chemistry lab, we have a little object that will actually sterilize the safety goggles. And so we pop them in there, turn on an ultraviolet light, it kills the germs. We have bug zappers. A lot of bug zappers use ultraviolet light because mosquitoes and certain types of flies are very receptive. They're very attracted to a very specific frequency of ultraviolet light. Forensic investigations. If you want to find out if there is perhaps a residual blood or some other bodily fluid on a surface, we can take an ultraviolet light, sometimes called a black light, and actually shine it on a surface, and we can actually see the residue from that using the UV light. And of course, we have X-rays as well. We use those for medical imaging to look at a broken bone and things like that. So in this series of videos, I'd like to wrap it up here by just concluding with this whole idea of waves. We started by talking about just generally what waves are, and then we talked about earthquake waves, and then sound waves, and here electromagnetic waves, and how when we think about these waves, we are actually able to learn some of the forces inside our planet, things that are actually able to help us understand where earthquakes come from, how to even predict, or at least, if not predict, sense earthquakes a minute or so ahead of time. These earthquake early warning systems can actually save lives. Our understanding of waves is improving our society. We're actually saving thousands of lives with these new technologies. Sound waves. It helps us to understand how animals are able to find food. We talked about how bats use echolocation, and we kind of mimic that same process in sonar, like on a submarine or something. We can also talk about hearing damage, why you need to wear earmuffs or hearing protection sometimes. It all has to do with waves. We talked about light, types of light, electromagnetic waves. Knowing about waves helps us to understand how the universe works. We now know how we know the universe is expanding. This is not just something that we pulled out of thin air. We actually have observed this based upon the Doppler effect and redshifting, something that we are kind of familiar with if you've ever heard an ambulance. So waves are very important to us in our everyday life. I hope you enjoyed this video. I hope you enjoyed this series of videos. If you did, if you'll smash that thumbs up button, I would really appreciate it. And hope you have a wonderful journey through science. I'm Jeremy Krug. Thank you for watching this video, and join me again where we can keep learning science together.